Hi everyone, this is Piers Ridyard, CEO of RDX Works. I'm here with the founder of RDX Works, Dan Hughes, and we are going to be doing a little of a mix-up today. This is the last AMA conversation chat thing that we're going to do before Christmas. So Merry Christmas, everyone.
Yeah, Merry Christmas.
I bullied Dan into saying that.
Yeah.
Very grateful.
I'm actually quite looking forward to my yearly visit from the Ghost of Christmas Past, Present, and Future. So that'll be fun.
Ghost of Christmas Past, Ghost of Christmas Future. Yep. And just reminding you to sometimes get out of the coding cave and that there is a world out there.
I know. I am getting out of the coding cave this Christmas.
There is a world out there, Dan.
I'm not going to be doing much.
Good. I'm really glad.
Going to get fat on pies and brandy.
You would have to try very hard to get fat.
Yeah. That's like
if there's anyone at risk of not getting fat, not at risk of getting fat, it's probably you.
Yeah.
Though you could probably grow like a very impressive little Christmas paunch.
Probably, yeah. But then I would just look like the Grinch because it would be just a disproportionate pot belly, and I'd be green from all the mince pies because of the knock me sick. So I probably would look like the Grinch. I might try that. It sounds fun.
So we don't have that many like AMA questions this week. So I thought we'd do like a combination of the two. The first ones are sort of like some questions that have been touched on before in the Telegram channel. But I thought we'd sort of like do a little bit of a double click on these ones and go a bit deeper. And then the other thing is you've been doing some interesting stuff with Cassandra. There was some extra stuff around running Twitter and Flappy Birds and a few other things. And some people in the community were even running it on like some Raspberry Pis. And I think it'd be interesting to sort of talk a little bit about what that is demonstrating and like how that's working and all that kind of stuff as well. So
yeah.
All right, so let's go on to the first AMA question that we have, which is why, if every transaction is multi-shard, so talking about Xi'an here, talking about network that's going to be released in sort of a couple of years' time, why, if every transaction is multi-shard, would you not end up with a increased finality due to increased numbers of shard groups?
Right, so you do. This is the thing, right? So we talked about the finality quite a lot in these AMAs. It seems to be like a recurring topic that comes up. So you absolutely do get a latency penalty when you're talking to an increasing number of shard groups, right? So, but it's not strictly linear because of a few things. So let's say that you had a transaction that was self-contained within a shard group, and let's say that argument's sake to 10 seconds, right? And then you got two shard groups, 20 seconds, and 3 30 seconds, and 10 100 seconds. It's not linear finality growth. It looks more like a logarithmic curve. So the difference between, say, a 3 shard group transaction happening and a 10 shard group transaction happening is quite small, maybe a couple of seconds tops. And the reason for that is because of the way that the mempools are synchronized between the various shard groups, right? So what's going on in the background is when I receive a transaction as a replica or a validator, and it goes into my mempool, I can see from that transaction what states are going to be changed, what it's trying to do, etc. And from that, I can look at the network topology and go, okay, so this transaction is going to touch shard groups 1, 3, and 5, right? And then the other replicas and shard groups 3 and 5 get the same transaction and they can see the same information, right? So what happens in the background is then I'm looking at my entire mempool and I'm saying, well, I've got this transaction and I've got a bunch of other ones that are going to touch shard 3 and I've got a bunch of other ones that are going to touch shard 5. So I will just signal that I'm ready to process these to those other shard groups, this batch of transactions that I can see in my mempool, and let them know I'm ready when they are, right? And then shard 3 is doing the same and shard 5 is doing the same. So what you end up with is this kind of loose synchronization of all of the shard groups across a set of transactions are saying, I'm ready for this, or I'm not ready yet, wait. Well, essentially, if I don't hear from them, they're not ready yet, right? So you get this loose synchronization across these shard groups. So the real latency only really occurs over a few shard groups, because you're going to be sending out these kind of, I'm ready to do these transactions to a bunch of shard groups, and the transit time for those messages, they're all going out at the same time. So that's why you get this kind of logarithmic finality curve, because everybody across all those shard groups has said, I'm ready. So they're loosely synchronized with each other. So if I then execute this transaction, then everybody else who's involved in this shard group have already signaled they're ready to do so. So they also will execute it a short time later, right? And that short time later is looking to be within around about a second. So it's quite responsive. But obviously there is quite a big hit between if I'm doing something that's self-contained within a single shard group, right? Because it's all local. So I'm not doing any external communication. So finality time on that might be, just a couple of seconds, very quick, because I'm talking with my local group. Whereas then I add another shard group, which is like your, basic transaction, right? I'm sending you some tokens, and it's going from, I'm sending you something from my shard to your shard, right? So then the latency hit, the finality hit there is quite big, right? That might be another 2 or 3 seconds, because now we've got this cross-shard communication. But then if it was a 3-shard group, the additional hit is much smaller. It's maybe then only a second, because while I'm talking to you, I'm talking to the other set as well. And then so on and so on and so forth. And it essentially just flatlines out at about 10 shard groups. So yes, you do have an increase in latency, but then that's just a limitation of that anybody would face that's doing cross shard, right? Because you've got to have this communication. You've got to synchronize what you're going to do next as a group. If you didn't have that synchronization step, which is quite critical, really, then I might be ready to do something, but I don't know when shard group 3 is, and I'm just going to be waiting and waiting and waiting and waiting. And if shard group 3 never actually pick it up, maybe they didn't even see the transaction, right? There was a communications failure. I'm just waiting around, and I don't know if they've seen it or if they haven't or whatever. I don't know when I can execute, when I can't. And obviously, this kind of setup is I don't want to call it a trade-off, because it isn't really. I don't perceive it as a trade-off having this additional latency, but the alternative is that you stick everything on a monolithic ledger, and then you smash into this upper throughput bound, and your machines have to be ever more powerful to be able to keep up with the load of just this monolithic.
Right. So the alternative is the way that Polkadot works or Ethereum works, where you have this sort of like the beacon chain.
Yeah.
I can't remember what they call it in Polkadot. But
it's a different name everywhere. You got C chains, all this stuff.
Right. Or Avalanche have a similar thing for their token chains and stuff like that, where you are essentially, you have to communicate to a chain that is then responsible for the cross-shard communication, essentially, and then that then becomes your bottleneck. And as as pointing out here, there's several things that are in favor of this method. The first is that everything's in parallel, so you aren't actually waiting for any transactions to occur. There is no single chain that I have to make sure that my state update goes into for any other chains to get any other subnets or whatever to get the update about that thing. I am independently coordinating it with the shard groups that matter and the nodes that matter for that particular thing. But in the interim, everything else in the network is carrying on in parallel. So there is no bottleneck that occurs as a result of that.
Right. So in any particular moment, me as a replica, I'm processing, voting, executing, whatever, any number of transactions, right?
Right.
Because those processes are asynchronous from the actual consensus process. Because the consensus process is just, do we agree on this? Did we agree on that? Right. And your execution can just sit at the side and do whatever. Right. And you can orchestrate the responses and the voting to arrive at a quorum agreed decision that you then push back to consensus to say, this is what we agreed on, please make it final.
Right. And this sort of like concept of something going logarithmic as overhead is in some ways also part of this idea of parallelism as well. Like there's the I don't have to talk to this group and then talk to this group and then talk to this group.
Yeah.
And then talk to this group. All of the groups that are necessary, talk to them all simultaneously. Yep. You have extra latency that comes in just as a result of probabilistic wait times on a network. The more nodes you're talking to, the more likely there is going to be some delay in response by one.
There's
subset.
Also another caveat as well, right? Is that if I'm ready to execute something and some of that state lives in shard 5, but shard 5 are already doing something with that state, then I have to wait for them, right? So you can get this kind of lock latency, right? Where even though the communication latency goes log, I might have to wait for them to finish, and everybody else who's looking at this transaction, right? I've got to wait for them to finish, and then for them to go, yeah, I'm ready now, guys. Let's do it. So you can get these spikes of latency under those conditions, but that depends on what it is you're doing, what the application is, and all this kind of stuff, right? So ignoring all that application domain latency that you might get for various things, just from a pure kind of consensus mechanism, it's very log, right? The more you pile in, the less it costs you to get finality.
Right, and that log scale that sort of goes that goes up quickly and then flattens off as you add more groups is sort of part of the beauty of having that huge shard space and the parallelism of it, because that is essentially your maximum constraint when it comes to throughput, rather than a single beacon chain or something like that all state has to go through, which then has its own constraints in terms of how much space there is in any given block and how quickly the network can process.
Your throughput graph is linear. It's your finality graph that goes log, right?
Right.
So your throughput graph, so your throughput graph is linear based upon the average number of shard groups a particular thing is touching, right? So obviously the throughput of the network, if all the transactions were 10 shard, would be a less steep linear curve, not curve, a line, right? It's linear.
A linear line.
Yeah. I mean,
there's unusual types of lines.
It's still linear, but it's just your angle of linearness is either it's more acute or it's not, depending on what your average workload looks like, right? Right. But then your finality time isn't interested in what the average workload is, because it's just specific to that particular transaction, right?
Right. So I mean, I think it's a fascinating bunch of you, and as you say, it's not so much compromise. It's that you're just sort of dealing with some fundamental truths of physics and network topology, and just given those constraints, a set of ways in which we have optimized. So the incredibly large shard space, making sure that you can have a large number of events in parallel, that there's as little waiting as possible for consensus to proceed on any given state update.
But the interesting thing with this is that if you scale a network topology up from a monolithic point of view, right? So if you were doing BFT deterministic consensus, which is one part of what Cassandra is doing. Obviously, it's a hybrid, but there's still that BFT part there where you're sending votes around to build a quorum, right? Now, if you weren't sharded, but you wanted to have, say, 1,000 validators in there, then your finality time for a particular transaction approaches, if not exceeds, the way that Cassandra does it, because you've then got to wait for votes from all these 1,000 validators, right? So if you were to take a monolithic chain and say, okay, I want 1,000 validators in there that are all going to vote, then the latency would creep up towards the same levels of latency that you would see in Cassandra for that same transaction, right?
Right.
Because it's not so much the sharding which causes your latency at those kind of scales. It's just you got to wait for a number of votes to go around, right? And there might be all manner of latency types to do with that, such as Raspberry Pi 3 might be in there, so it's a bit slow, or someone's connection might be a bit on the slow side, or someone's busy dealing with something else or doing a garbage collection or whatever, right? It could be a million different things that cause latency at that scale. So when you have validator sets of that kind of size, most of your latency comes from other factors and not the fact that your consensus mechanism, right? You're just waiting for a larger group of participants to state their opinion.
Right, and you can see that sort of problem in happens in Avalanche as well. Like they had quite a lot of issues with latent voting nodes. I don't know if it's still a thing, but there was like this period where people were running because they were like, "Oh, you can run Avalanche on Raspberry Pi," and then they were running on a Raspberry Pi, and then the network was being latent, and they were like, "Oh."
Yeah, I mean, there are limits, right?
Right.
I wouldn't suggest that people actually run full node consensus on Raspberry Pis, but
No. And that's part of the reason that even today, the incentives on the network, we have this sort of like rapidly decreasing staking rewards based on missing rounds of voting, which is essentially a quasi latency thing. Like if you're online but respond not within time to a vote request, then you're essentially marked as not present, missing a vote, and the economics of the system, the way that you've created the proof of stake rewards, should basically nudge your validators towards the kind of behavior that helps make sure the network behaves in the best way possible.
And normalize the hardware spectrum. Right? If everybody's faster than me and I'm slow, then they're gonna process proposals at a higher load than me, and I'm not going to be able to. So I'm going to get penalized. Right. So I need to buy some better hardware. But at least your hardware is normalized, and there's no minimum bound of you need to have this warehouse of hardware to keep up with the network. So.
Right, and at least when you get to Xi'an, like you have this. There's like you can have a small computer running on it, but your small computer plus your internet connection needs to be sufficiently good to be in any particular validator set. Otherwise, you're going to start missing proposals as well.
Yeah. Interestingly, I know we're going to get to this in a little bit, but this is kind of interesting now. I suppose it's relevant. So, like the Pi 3 that was in one of the Cassandra tests last night, even though it was keeping up and it was able to participate in consensus. Because it wasn't as powerful as the kind of mean of all the machines in there, and because obviously Cassandra is leaderless, right? The way that you acquire influence, stake, reputation, whatever the model might be, is that the Pi 3 it was always falling behind in terms of, okay, what's my influence in the network, right? Because I can participate and I can vote, but I'm not able to because I'm so slow, my proposals that I'm making aren't getting picked up by everybody else in time before they've moved on, right? Because everybody's got much more responsive liveness than me. So I can keep up with the network, but my proposals just aren't getting there in time because I just don't have the compute to make them. I don't have the bandwidth or IO or whatever. And so you see that the influence ratio of that Pi drop, which is kind of a natural kind of emergence of what you were just saying, right? Like I'm dropping down, and so if you were to say in that environment tie the acceptance of a proposal to some reward, well, the operator of the Pi 3 would like, okay, I need to upgrade my hardware here because I can keep up, but I'm not able to take the lead with my proposals because I'm just not fast enough. So if I want those rewards, if I want to be not missing proposals as it were, then I need to upgrade my hardware. So it's quite interesting how that behavior comes about in certain situations.
Super interesting. The other question is, and it's sort of linked to the first question in some way, why does the shard space not need defragmenting?
Does it need defragmenting because there's so many of them?
So just for those people who don't automatically know what defragmenting means, what does the question mean?
Okay, so I'm going to assume this is the question because this is usually what these kind of questions mean, is that I've got some transaction, I've got some, tokens that live in a particular shard, and then the network is so busy and there's so many people using it because we've taken over the world, that other people's transactions are ending up in my shard and potentially conflicting with my shard, my transaction in there, and my balances, and it just becomes there. So defragmentation is, I'm guessing, okay, so these old transactions that live in these shards, get rid of them because they're getting in the way of the new ones and causing conflicts. Now, that's not required. We don't need to do that, because the shard space, 2 to the power 256, is so insanely big that if ever there was a conflict of shard space, number one, I won't be around to see it. Tell you that much. Even if we were doing 1 trillion transactions a second, none of us alive today would see it. Right? The probability of
I feel like this may be one of those like Bill Gates predictions, where Bill Gates is like, I don't see why anyone needs more than 2 megabytes of RAM.
You can run the numbers, and 1 trillion years is probably quite pessimistic, right? It's probably an order of magnitude or two above that. A trillion transactions per second or whatever. It's so huge, and even if that did happen, then the solution to deal with it is actually quite simple. You can have multiple things live in a shard, because the point is they are independent, right? These two things are independent. They don't have any relationship with each other at all. So you can actually handle multiple substate audits, if you like, occupying the same shard, right? The pigeonhole principle isn't a problem here. Back to pigeons again. So you don't really need to defragment. I mean, like if you were a low power node again, like a Pi, right? You might want to prune off some of the old stuff, because there's plenty of copies of it around in the network already. So you could prune it off if for storage use if you wanted to. But from a purely kind of theoretical point of view, it's not a problem. And the reason it's not a problem is I think it was Scott, the Wolf of Wall Street, the other day. I think it was either him or Pomp made a statement that the current difficulty in Bitcoin is like flipping a coin 70 something times and getting heads every time, right? So the probability of a collision in our shard space is the same as flipping that coin and getting heads 256 times.
Mm-hmm.
And that may sound not like a large increase. Well, it's 72 and 256, but in the case of like a power of 2 number, such as 2 to the power of 256, every flip, it's like, okay, so the probability of that happening and coming up heads is a multiple of the one before by 2, mm-hmm. right? So 72 and 256, it's not like, oh, well, it's 3 times larger. It's a lot larger, like a real lot larger. And things like another way to comprehend it is that
it's 2 to the power 184 larger, right?
There you go. Right, lots larger. And like things like it's like me and you going to a beach, and us not being aware of each other, and we both try and pick up the same grain of sand, right? Mm-hmm. It's like and that's only, what's that on a beach? It's like 2 to the power of 60 maybe. So I don't actually know how many grains of sand there might be on a big beach. Maybe that's on the planet, but whatever, right? It's like us just picking up the same grain of sand, right? Just
so
random.
Highly unlikely. So collisions are highly unlikely. Let's take it from the other direction. So that's
actually a really good analogy for a collision, right? You put 2 people on a beach, mm-hmm. and then you tell them both to go pick a grain of sand, and they both, without knowing the other is there. So I've got Harry Potter invisible cloak on, and you've got one too, and we both try and pick up the same one. That's like insane.
Right. Or get someone to go onto a beach first, pick up a grain of sand and drop it, and then then
somebody else picks up the exact same grain of sand.
What's the so taking it from the other approach? The other approach would be the other formulation of this question would be, if every transaction is cross-shard, and I have a token, and that token starts off as being, as being on a shard, and then as I spend it, it goes across, it increasingly goes across the shard space of all of the outputs and all the addresses and all that kind of stuff. Do you not need to at some point start do you not need to defragment it from that point of view, where you've got the token is just too spread as dust across too many outputs, and so now spending one of these tokens suddenly ends up pulling in large numbers of node operators and large numbers of shard groups with every single spend?
Well, that's just the dust problem of using a UTXO thing, right? So it's you have the same problem in Bitcoin, right? If you want to spend a lot of dust, then it's going to cost you, and the fee is probably going to cost you more than the amount of dust that you have, right? Because you're pulling out all of these little bits and pieces of outputs. So it's not really a shard problem. It's just a dust problem. It's just the dust problem, and it's one of the downsides of having a UTXO style state model. Right. But in this kind of environment, this kind of sharded environment, it's much simpler. It's easier to manage than to have, cross shard balances and stuff, right? Or balance that has to move because then the account state has to move with it, stuff like that. So
your cost of fixing it is lower just because of the throughput of the network and the transaction, but you can still end up in the same situation where sort of gathering the dust is more expensive than actually the value of the dust.
Yeah. I mean, you could do it and just, you could have a kind of special transaction, right? Which is okay, I want to gather all this dust. You validators just do it whenever you feel like it, off peak or something, right? It's if you've got nothing to do,
garbage collection.
If you've got nothing to do at some point and you've got idle thumbs, then you could just do this for me, and I'd be very grateful.
It's one of those problems that is it's intellectually interesting, but it doesn't matter. It doesn't matter. The fact that a token is spread over a very large proportion of the network doesn't matter.
No, it doesn't. And I think the main issue with the dust problem is it's not so much the dust or the sharding; it's just demand for space. Right. So, in Bitcoin, it's prohibitively expensive for me to collect all my dust because the demand for that one and a bit megabyte of block size is so high, right? You've got the fee markets going on. But if you've got extremely high throughput, then the demand for space might be very high, but the supply of space is also much higher, right?
Right.
So in there's a possibility where collecting dust from all of these shard groups actually isn't prohibitively expensive, and you could do it. And then because you can linearly scale our technology, then I would argue that it should never become prohibitively expensive to be able to do that.
Well, I think there's always going to be a point where it is, right? There's always going to be a point where the dust is less valuable than the transaction fee for any given transaction. That it just
potentially, well, just talking about it from a supply and demand, raw supply and demand point of view, right? Then that's really the main problem. There's demand for something and the space is scarce. And so for me to collect this dust costs too much because of the fee market, right?
Right.
So
I also I personally find it really difficult to visualize 2 to the power 256 as we've been saying versus, a million or a billion. It's how many addresses is this wallet spread over? A billion. Isn't that a problem? No, you've got 2 to the power 256 shards.
Yeah, I mean, you can get close by writing 1 and then 100 zeros after it.
Okay.
That's close enough. It's actually 10 to the power of 80 something. So you'd have 1 and 80 zeros. That's how many shards there are essentially.
That's a couple of. That's
a big number.
That's a big number.
It's a big number.
Cool. All right. Well, let's go on to you. You've done a couple of new Cassandra demos, which have been sort of
kind of unexpectedly it turned out as well. So we ran some Cassandra community tests this week because I had a couple of things that were frustrating me. One of them, I'm pretty convinced, is just some wacky configuration on one of my nodes, one of my validators that I've been using for testing. It was just doing some weird stuff with networking, but then I couldn't seem to get rid of it, so I wasn't sure if it was a code problem, a my problem, or whatever, right? So we did a couple of community tests to help me nail that down, and a big shout out to Robin in the community who loaned me a few of his machines for a few days because the problem was also they seem to be catalyzing the problem on my end. So thank you very much for that. Let me take those off your hands for a few days and use those, because this was also a problem. I couldn't reproduce it very easily either. So but his hardware allowed me to reproduce it like that, which was very helpful if you're a developer. And then you're very aware that not being able to reproduce a problem consistently is the most frustrating thing in the world. It's like, oh my God, I've run this 10 times and it's only done it once. How on earth am I going to debug it? So thanks to him. Unfortunately, it seems the problem is definitely with the hardware I'm using, so I don't know what's going on with them. And then something else that I wanted to try out, and just kind of get the Cassandra code base reliable, so that I can start to run some really nasty edge cases with it. But I don't want to get to that yet until I'm sure that my kind of baseline is good. Otherwise, it just poisons the output if there's still other things going on. And so they've just been testing a bunch of things. One of the things that came out of that was obviously the Pi 3 stuff that I was tweeting about last night, because there's a chap in our community who occasionally joins. And I didn't even know it was a Pi 3 until last week. This guy joins the test sometimes, and his
basically trolling you.
Yeah. And his validator always seems to like run a bit slow and just lag behind everybody else a little bit. And I just put it down to, it's an old laptop or he's got a slow connection or something. And then it was revealed last week that it's actually a Pi 3. It was like, okay, that's Pi. It's only the latest one. It's like a Pi 3 with a 2 gig of RAM or something, whatever it is. And so he joined again last night when I was doing one of the things that I was doing aside from these kind of fixing and bugs and reliability things. I wanted to see what the intricacies would be of being able to update part of a DApp, right? So I've got a DApp and there's a bit of code in there. Script or whatever, right? It doesn't really matter. It was just more of the principle of how would you update something and make it secure and have like an audit trail of the updates and stuff. So I've got some DApp and there's a bug. I want to fix the bug. Am I able to just update that part of the code and have like a kind of proof and an audit trail and stuff for that and all these things? And so that's what we were testing yesterday, because I wanted to make sure that some of these other kind of endpoints that we were using where we can go to the DApp store, run Flappy Bird and Twitter and whatever, they could see the updates too and how responsive were they and everything. And this Pi 3 turned up again. And so I was playing around on its endpoint and it was doing full consensus. It was handling the tweets that were being imported and all the updates, and it was hosting Flappy Bird and my website and the DApp store and Twitter and all these other things and images and stuff. And it just was like, wow, this is actually really cool that this Pi 3 is able to do all of this. And I believe it was only running at about 60% CPU utilization as well, because he did some benchmarking on it. And the Cassandra code base is very far from being optimal in terms of performance. So, it's doing all this BLS state vote stuff as well. And like BLS is renowned for being extremely expensive. And Vitalik and other people have written many posts about how to optimize BLS and how expensive it is to do it. So the fact that we had a Pi 3 doing all the BLS stuff, running it, I think we were doing like 50 transactions per second. So not very fast in terms of, breaking any records, but Pi 3 is doing 50 transactions a second with 20 or so other nodes in the network doing all the BLS stuff and consensus.
How much of the shard space was the Pi doing?
So the test that we started the test yesterday with 4 shards, but then I bumped into this networking thing again on one of my Bootstrap nodes. So I thought, you know what, let's just simplify this test and see if this gives me any more new data on that Bootstrap. So we actually just had it unsharded. We just ran unsharded, so the Pi was serving everything as well. So the load was a bit higher than it would have otherwise been, I think, for that kind of throughput. But then that did actually end up giving me quite a bit of information that I can hopefully use to figure out what's wrong with these 2 Bootstrap nodes that I'm using. It always seems to be the Bootstrap nodes as well, which is strange. So it wasn't a sharded test, but even so, I don't think it takes anything away from the fact that that Pi was able to keep up with everything that we were doing. It was fine.
That's awesome. That's really awesome. So like, Cassandra has been running as like this test bed network for you for quite a while now.
Just over, I started it just over a year ago, but it kind of officially became a research network, I think, in January-ish of this year.
Right. And I suppose looking back over the year, what have you discovered, and what have you sort of done? Like, how has the network changed since January? And like, what's been that sort of like? It'd be really interesting just to sort of do like a look back, rewind on the network. I'm sorry, just for those people who don't know, Cassandra is Dan's research and development network. It isn't ever going to be a production network. It's a playground to basically prove out some of the ideas that we have for our advanced consensus research, our advanced network research, that allows us to sort of learn in a sandbox environment, important things that you don't just learn from sitting down and doing the theory, or sitting down and running it on like a single node or a little cluster. It's about experimenting.
He makes it sound like a toy. This is no toy. This is a big gun that will give pretty much any of your top 10 actual launched mainnets a run for their money across a broad spectrum of things. So it's dangerous. it's definitely dangerous.
Advanced weapons research.
Yeah, it is. It's like a gaggle of howitzers parked on a hill that nobody's noticed yet down in crypto Twitter, and I'm going to start firing them real loud pretty soon. But I mean, it's interesting because like from the main things that have changed have been a lot of the peripheral stuff, right? So the kind of idea of, okay, I want to do this kind of hybrid, leaderless, permissionless, kind of sharded network that, takes something of Cerberus and does something with it. The actual initial kind of ideas of how that would work, the kind of block tree and the POW, and then that feeds into a deterministic phase, and you've got all this state probe stuff going on. That actually hasn't changed. That appears to have been bang on the money from a kind of broad architectural point of view, which has been handy because I really wouldn't want to go and revisit all of that. But it's been like all the bits and pieces that sit underneath. Like, okay, how do you select which branch you're gonna jump onto, right? Because it's not just as simple, because there's the combinatorial power stuff in there as well that is used in part to select the branch that my particular set of replicas and validators is going to follow, right? And there's just been lots of bits and pieces that have been close, but not quite there. So the kind of broad architectural vision is correct, but then selecting a branch is a little bit more intricate than just, okay, which has got the strongest power, right? You need to consider, okay, well, do any of them have a potential super proposal already? A super proposal being where you've got 2f+1 of your validators have voted on it, right? Because if you have that super proposal, then no matter how strong this branch might be, you need to ignore it, right? No matter how much power it's got, because look, you've got a potential agreement over here, right? So ignore that, and then little tweaks to that and sticky proposals and all these things, and like the mempool synchronization we were talking about earlier on, that was lifted straight from from tempo when I was playing around with, okay, the issues with tempo, how would you actually fix them? So over the course of a couple of weeks, I just messed around with that just for my own peace of mind, and that was the main thing that would, fix those tempos issues that we had. And that's in Cassandra, and that provides all the loose synchronization for the mempool stuff. And that code, other than just little tweaks and, things here and there, that code hasn't changed either. So, and the block tree stuff is still largely the same. So it's like we had all these components floating around already, and there was just this kind of ding on, okay, glue all these together in this way, take some bits from here, take some bits from there, get some Cerberus bits in here and whatever, and you end up with this network. So the main piece of work, I think, has really been the state vote stuff. That's probably been the main.
My favorite thing over the entire year was still where you called it when we were talking. You're like, Piers, I've just added bloom filters, and I'm like, you're going to take them out, and you're like, no, they'll be fine.
No, they're still in. They're still in. They are still in because one of the things you've got an information problem, right?
I do,
this is why a lot of sharded chains have like a main chain, a beacon chain, or whatever, right? Because the problem is, if you're doing true sharded in the way that we are, like state sharding, right, is that if I'm communicating with your validator group and you're voting on some stuff, then I have no idea who constitutes a supermajority over in your shard, right? So it's like, well, how much stake have you got, or reputation, or influence, or whatever, right? So if I receive a quorum certificate from your shard that says, hey, this is a 2F+1 supermajority, I'm like, well, how do I verify that? I need to know who are the constituents and how much vote power do they have, basically. Now, most of that gets pushed off into like a beacon chain or a main chain or whatever you want to call it, right? But the problem with that, of course, is that can get bottlenecked if you've got lots of shards and everyone's sending proofs there for this is how much vote we have, how much vote power, etc. So I didn't want that because that's a crappy solution. So the bloom filters are actually used within the quorum certificates to carry that information of who has what vote power in your shard. And the nice thing about it is that because I have a tolerance of error, which can be up to F, it doesn't need to be 100% accurate, and it doesn't need to be 100% up to date. Right. So that's where my bloom filters still are. So they're still there, Piers. I didn't take that.
Yeah. But it's just like, I feel like you're constantly, since before I was with Radix, and then since with Radix, it feels like you have a jigsaw puzzle, right? And you've got all of these pieces, and you sit down and you put together, and different bits of these pieces are like bloom filters and BLS signature aggregation and vector trees and all of this kind of stuff. And this is sort of like all these puzzle pieces have just sort of like grown over the course of the 9 years that you've been working on Radix. But like there are reoccurring pieces that I see. They are
consensus
trees
Lego
being
bricks.
One of them, like bloom filters being another. And I remember the first time you told me about bloom filters is probably 3 years ago, and you're like, oh, there's this thing called bloom filters. And I was like, oh, what's a bloom filter? And you're like,
I love bloom filters. I love them. They're extremely useful, and you can make them like strongly cryptographically provable as well, while having like a Merkle tree behind them too, which is also quite compact. So
yeah,
I love bloom filters. They're great for all kinds of stuff.
But like the whole like definitely no or maybe yes thing around them, like that being like such an intuitively nice feature, but also like an intuitively frustrating feature, because it's like I get definite no, but sometimes I just get maybe.
Yeah. You have to know how and where to use them. And yeah, because if you use them the wrong way around in the wrong place, then they don't act. They can make it more expensive, right? Depending on how you're treating the yeses and the nos. Sometimes you can't put them into that yes or no question, and sometimes you can. Depends what you're doing.
Right, and so like it's just enjoyable seeing all of these things like sort of be brought back into a more and more complete picture. that of like how this whole system works, everything from sharding to consensus to mempool synchronization to vote aggregation to network latency and topology, all of this stuff that has just been like this huge amount of research and development and understanding of what is the cutting edge of computer science, and sort of like just bringing it together to create this research project.
You actually might like the way that I'm using the Bloom filters for the
go on, tell me.
For the vote power, right? So with a Bloom filter, you ask it, is this in there? Yeah, yes or no. So if I've got a Bloom filter and I want to find out your vote power, then if I say is peers in there, it just says no or maybe yes, right? But I don't know what your vote power is that's been communicated. And then if I say, well, does peers have a vote power of 100? It'll say no or maybe yes. Okay, well, does it have a vote power of 101? No, maybe yes. And it's like, well, what is his vote power, right? Well, your vote power could be in the millions, right? So I might ask this Bloom filter 1,000,000 times before I actually figure out that your vote power is maybe 1,000,000, right? I don't even get a strong yes out of it. I just get 1,000,000. So instead, the way I do it is I encode the binary representation of your vote power into the Merkle and into the Bloom, and then I say, does peers have a vote power of 1? And it says no, maybe yes. Well, that's okay because it's a binary question, right? So it's definitely either no or yes. Yeah, and then I say, okay, does peers have a vote power of 2 in binary? And it says no or yes. Maybe yes being a 1, right? Then I say, does he have 4? Does he have 8? Does he have 16? Does he have 32? And then I ask all the way up to, say, 32 bits, and then I have your vote power. Exactly your vote power. Not just a maybe. I know exactly your vote power.
So you've like, again, it's a logarithmic.
No, it's a linear question.
I know, yes, sorry. Question, so yeah, but it's a logarithmic answer. Yeah, it's really interesting.
So I can embed your vote power in binary form and then use the no, maybe, yes in terms of a Bloom filter to tell me. And if somebody else is also in there and kind of occupies the same slot, it's okay because I've got an error bound of F that I can use, so it's fine.
I also enjoy, like, the other thing I've enjoyed over the years is like the realization of like how much data packet size, like my concept of data packet size is completely warped by what I'm used to consuming as a consumer, right? So like, oh, it's a 2 megabyte file, who cares, right? Whereas in a network, it's like, oh, it's 2 kilobytes, that's a problem.
Yeah.
And it's and so like that sort of like what you're talking about here, like going right down to binary representations of something and then using a cryptographic proof against that binary representation really matters when you're dealing with sort of very large network topology, very large number of nodes, very large numbers of messages. That's also been fascinating.
Yeah, because those hundreds of bytes add up real quick. And then you require 100 megabit connections plus to just tick along at 100 TPS or whatever.
So with this particular testing that you've been doing, you know, sort of towards the end of your this phase of research, what have you been trying to show with these last latest tests?
More so just to get it reliable, right? So I've done all of the non-critical kind of complex edge cases, right? So let's cause a liveness break. Does it resolve? Let's try and cause a safety break. Can I catch it in the primary phase? You know, how efficient is all the state vote model stuff? Can I yank validators out of that state model mid-vote, and is my bound actually still F, or is there some, you know, variation of that because of various things going on, like mechanics and stuff? And so all those kind of like, you know, fundamental tests of does this theory stand up under somewhat adverse conditions, right? How does it hold up there? Can I recover from these things? Are these things not a problem? Is it meeting the expected bounds, etc.? Right? And that's all good, which is great. But then there's a bunch of other really like a lot tougher, a lot stronger attacks and security testing that I want to do on it. That the theory should hold up against, right? But obviously I want to empirically test it as well. But to get to that point, I really need a reliable code base, right? No bugs, basically, or as few bugs as possible. Because what I don't want to do is run one of these tests. There's some unknown, there's a bug that's causing an output that is incorrect, and then I spend 3 days goose chasing around some theory to find out, it was a bug, right? So that's really the phase now. Is okay, let's just get this code base reliable. All the little minor bits and pieces that we've been able to ignore because we're not doing that critical side of the testing, we need to now clean them up. And so that's hopefully where I'm going to get to, either this side of Christmas or early on in the new year. And it's getting there. Like the tests yesterday were very encouraging. There's only really a few things that came out of that I need to fix. So we should hopefully get to that pretty soon. And then I can really start to dig into, okay, how do I actually cause a safety break here, right? How do I get around this inherent resistance to even safety breaks, let alone liveness breaks? And how do I break it? And I've got some ideas around how to do that, because no network is completely infallible to a safety break. But what you can do as a protocol designer is you can move the bar where the adversary needs to be, right? So you can say, okay, well, if you cause a safety break, you've got to do all this. You've got to be just like mega powerful, God-seeing eye kind of thing, right? And even under those conditions, like at that point, you're moving it into logistical effort and maybe monetary effort, right? Not so much from a theoretical point of view, because from a theoretical point of view, any adversary can always win eventually. Yeah.
Right.
But it's, what will it cost you? Is it worth it? How difficult is it? What are the impractical things that you've got to try and overcome?
Yep.
So that's where we'll be next.
Very interesting. Awesome. Well, it's been awesome talking with you, Dan. Thank you so much for giving us that rundown on Cassandra. And I suppose Merry Christmas to everyone in the community, and thank you so much for your attention and support and questions and love and general, like I'd say the main message from me is download Scripto and get building.
Alexandria's out tomorrow. Yeah, that's something for you all to play with over Christmas. But if you have any support issues, it's tough because most people are off.
Yeah, so it's like there will not be very many people around, but we hope that there is enough in all the documentation and everything that we've done to sort of have a really fun time
to see if the documentation's up to scratch. If January comes and no one's built anything, it's not. If January comes and like Ethereum's ecosystem has been built over Christmas, then docs are all good.
I would be very sad if no one built anything. And there is also like the NFT implementation that they've done is unbelievably cool. Like it's so freaking cool. So yeah, I'm looking forward to people playing around with that too.
Cool.
Alrighty.
All right, guys. Well, see you next year, unless you catch me on the socials, dotting around. A good Christmas. Drink lots. Have nice presents. Get fat. And then go on a diet in New Year.
Yeah, I want to see everyone's Christmas paunch.
Yeah.
Cheers, guys.
Ciao.